So far, we have talked about the current and the voltage in AC systems, and how they are related by a form of Ohm's law that uses the impedance instead of just the resistance. Now we are going to talk about the power, and the power is a little bit more complicated. So I'm going to start off with a blanket statement that for any point in time, the power at that point in time is equal to the current at that point in time times the voltage at that point in time. P equals IV. Now, you may think that this is simple, and yes, this part is. However, this is known as the instantaneous power, and it's not typically what we are interested in. Usually, we are interested in something called the average power, the average power over a long period of time. For instance, when I plug my phone into the wall, I can say that my phone is draining, say, a half a watt of power. That's not actually how much power the phone draws at any given point in time, because my phone charger is highly reactive. But that is the average over a long period of time, over the however many hours I have it plugged in. So for average power, what we want to do is take the power of time, integrate it over a long period of time, and then divide by the total amount of time. So let's look at a few cases. First, let's assume that the device that is drawing power is purely resistive. That is, there is no reactive component to the impedance. Well, in the case of a purely resistive load, I and V are in phase with each other. We can say that V equals I times R. So I of t is given by this right here. V of t is given by this right here. So I naught times I naught, that becomes I naught squared, and this R. And then we have cosine times cosine. Now we can do the calculus, but the average value of cosine squared is 1/2, which means that the average power is 1/2 times this I naught squared times R. A few ways to think about that. That 1/2 comes from the fact that this I naught represents the peak, the maximum value of current. But because we're dealing with oscillating current, it's not always at that peak. And so the average is 1/2. And that 1/2 does come from the integration of cosine squared. Now, one thing we often see is this thing called the RMS. That stands for the root mean squared. Basically, you take this current, which is a function of time, you square it, you take the mean of that, or the average of that, and then you square root that value, and you get the IRMS. Now, so from this, we can see that the RMS current is 1 over the square root of 2 times the peak current. And writing it like that, we can say that the average power is equal to IRMS squared times resistance. Now, there's a few reasons for this. First of all, like I said, this I naught, that represents the peak current, but that current is larger than the current is most of the time. Now, we can't just take the average of the current, because this current is going forward as often as it is backwards, so the average current is 0. This RMS current represents a kind of functional average, because usually when we use current, we square it. So it's the average of current squared. It's very useful. Another reason why RMS is useful is because in class, we talk about currents and voltages as if they have this nice, simple cosine or sine functions. In reality, AC power is messy. If you were to plug a digital multimeter directly into the wall port, and by the way, do not plug a digital multimeter directly into the wall port, you wouldn't see a smooth sine wave. You would see something very ugly, very ripply. and it would have peaks all over the place, and it would not follow this cosine or sine curve at all. But you can still do an RMS to it. You can still take the power function, or take the current function, square it, average it, and square root it, and you would get an RMS current that, even though it's no longer sine and cosine, you can still use in this formula. Also, current isn't the only thing you can RMS. You can RMS voltage as well. And if you get into signals, there's RMS happens a lot there. Anyway, slightly off topic. Now let's imagine that our device from before was completely reactive. That is, its impedance was purely from the reactive component. There was no resistive component. In that case, we can still say that V equals I times, in this case, X, to get the magnitude of voltage, but the phase of voltage would be shifted by 1/4 cycle, which means cosine would turn into sine. And so your power as a function of time would be given by this formula right here. Now we still have I naught squared, and we still have the reactance of the component, but now we have cosine times sine. You can plug in a value of time and you will get power. So this component will at some times draw power, but the average is 0. Now wait a second. How can the average be 0 if I just said at some points in time it draws power? Well, that's because there are some times when it draws power, but there are also some times when it releases power. When cosine and sine are both positive, such as what happens in the first quadrant, then yes, this is a power drain. But when cosine is positive and sine is negative, or vice versa, this starts to act like a power source. And because it drains in the first and third quadrant, it's a source in the second and fourth quadrant, it drains just as much as it provides. There is no net power drain. Now, ask ourselves, what is a fully reactive device? Well, those are capacitors and inductors. Capacitors and inductors store energy. They don't drain energy. A resistor will take power and will convert it from electrical power to heat or light or something. A capacitor and an inductor will store that energy. So it kind of makes sense that at some points in the cycle they'll store energy, and at some points they'll put it back. All right, so this was purely resistive, purely reactive. Let's go for the combination. What if it is complex? Now, we could do a bit of calculus. We could say, okay, there is cosine, there's an extra phase difference. We could do all that integration. I'm going to do it for you. The factor of integration is this right here, cosine of the phase angle of the impedance. This, by the way, the cosine of phi z is sometimes called the power factor. A power factor of 1 would be purely resistive. A power factor of 0 would be fully reactive. And a power factor anywhere is just, or anything in between, is just a quantity that you multiply to get the average power. So we can go ahead and say that the average power is I RMS times the RMS electromotive force times this power factor. And we can use our Ohm's law to get it in other forms. We can say it's ERMS squared over Z, and by the way, this is the magnitude of Z. Since we're using RMS, we don't actually need to worry about the phase angle, except for where we are doing that explicitly. We can also use that the power is equal to I RMS squared times Z times this power factor. But if you think about how the power factor is defined, cosine of phi is equal to R over Z. So this all just becomes I squared times R.